Howdy Bike 410 students. So we were talking about the three definitions for KM. And I'm sorry, I keep touching the screen. And so that's what the slide that we ended on. And I just want to use that in this example shown here. So if we look at KMs for different enzymes, we can see that some KMs are large, and those are shown at the top. The larger KMs are shown up here. So like carbonic anhydrase has a Km of 12 millimolar. And then down here, lysozyme has a small Km. Actually, there are larger ones. Glutamate dehydrogenase has a high Km for some substrates and a low Km for others. So the point is you can have a range of Kms for different enzymes. But let's focus on carbonic anhydrase because I want to make a point about how good an enzyme is and its relationship to Km. So carbonic anhydrase has kind of a crappy Km, right? That is that there are 12 millimolar, at 12 millimolar enzyme and substrate concentration, at 12 millimolar carbon dioxide, carbon dioxide is a substrate for carbonic anhydrase, you have 1/2 of your carbonic anhydrase bound. Okay, that's the KD. That's what KD would actually mean. And KM is an approximation of KD. So that's pretty high. 12 millimolar. That's a lot of carbon dioxide that you would have to half bind, half of the enzyme that you have. So it's not a great binder to its substrate. So hold that in your mind because as we go through the other constants and what they mean, we're going to get to catalytic efficiency. And we're going to see that catalytic efficiency takes into consideration not just how well an enzyme binds its substrate, but also how well it does step 2, the chemistry, how fast it converts substrate to product. Okay? All right, so before we do that, let's look at Vmax. And this slide is similar to the slide that we ended the last video on. It's a summary slide of all the things that Vmax actually is. Remember, it is the theoretical maximum velocity. We're never going to reach Vmax because in reality, encounters between E and S are asynchronous. They're not simultaneous. So it's the theoretical maximum rate of conversion of the substrate to the product. And it's also a constant. You got to keep in mind that these constants that we have been talking about are like a fingerprint for your enzyme. Each enzyme has its own Vmax. It's a constant at a constant enzyme concentration. So this is important. It's one of the equations that you need to memorize. Vmax is equal to Kcat, remember that's K2, times the total enzyme concentration, which you know because you started the reaction with a given amount of enzyme. You put in a certain amount of enzyme at the beginning of your rate measurements, okay? So you can calculate Vmax if you know Kcat and you know ET. All right, so that's Vmax. Let's talk about Kcat. Kcat is the activity of one enzyme molecule. It has to do with that second step, the chemistry of the reaction. So going from ES, the ES complex, to E plus P is described by the rate constant K2. And K2 is equal to Kcat. Okay, so K2 is equal to Kcat, the rate constant that has to do with catalysis, the chemistry, which is equal to Vmax over ET because of the last slide. Remember, we said Vmax is equal to Kcat times ET. So that means that's just a rearrangement of that second equation that you have to memorize, okay? So for most enzymes, Kcat is a constant. So every enzyme has its own Kcat. And the range for Kcat can range from less than 1 product formed per second to many millions of products formed per second. Okay, so it's remember, it is the turnover number, turnover of substrate to product. So don't make this more complicated than it is. This fancy word turnover number just means a turnover of a substrate from its substrate geometry to its product geometry, conversion of substrate to product. It can be given in units of moles per sec, or it can be given in grams per sec, or it can be given in, whatever unit of amount per sec. So we usually just get rid of the unit of amount, and we just say per second. Products per enzyme molecule per second when the enzyme is saturated with substrate, because the rate of formation of product is a variable. That's the initial velocity. We're talking about the maximum velocity here. So the turnover number is equal to the maximum velocity divided by the total enzyme concentration. Okay. All right, so let's look back at carbonic anhydrase again. Remember how carbonic anhydrase had a Km that was kind of crappy? The Km was like 12 millimolar, which is a high number, and a high number means a weaker association, because a large dissociation if Kd is large, then the E plus S is the big arrow goes to E plus S. Okay, all right. So what that meant in the last table was that carbonic anhydrase doesn't get saturated until you go to very high substrate concentrations. However, carbonic anhydrase has a very high turnover number. And in this case, a large number means a large conversion of substrate to product per second. So carbonic anhydrase, which had a crappy Km, has an excellent Kcat. It's not as perfect as catalase. Catalase is a perfect enzyme because the only thing limiting catalase is how fast the substrate diffuses into the enzyme active site. Okay, so for a perfect enzyme, it's diffusion limited. But carbonic anhydrase, which was studied by the Russian scientist Oleg Petitsin, who pronounced it carbonic anhydrase, because Oleg Petitsin had a speech impediment in addition to an extremely thick Russian accent. But his slides were beautiful, so even though you couldn't understand a damn thing he said, you could certainly understand his genius by watching the slides when he gave a talk. So carbonic anhydrase has an excellent Kcat, a crappy Km, but we're going to see what defines how good an enzyme is a combination of these two terms. And that's called catalytic efficiency. So catalytic efficiency is the ratio of Kcat over Km. Now Km, when it's a good binding between E and S, you have a small dissociation constant. And since Km is an approximation of a dissociation constant, a small number in the denominator will give you a large catalytic efficiency. But the other way to get a large catalytic efficiency is to have a very high Kcat. So you can have either a high Kcat, in other words, lots of product formed per second, or you can have a very low dissociation constant, in other words, a very good capture of substrate by the enzyme, and that can help. That combination helps you to score one enzyme compared to another enzyme. The Kcat over Km approaches 10 to the minus, or 10 to the ninth, sorry, not 10 to the minus 9, approaches 10 to the ninth. It's more likely to be around 1 times 10 to the eighth, even for the most perfect enzyme, because that 10 to the eighth moles per second is about how fast a substrate can diffuse into an enzyme active site. Okay, that's what is meant by the diffusion limit. Now, catalytic efficiency is one of those equations that you're going to have to use on the quiz and the exam. So don't get it confused with catalytic power. Do you remember catalytic power? Catalytic power was the catalyzed rate over the uncatalyzed rate. So that's like how many fold faster the reaction is in the presence of enzyme compared to in its absence. And that also should be a large number because the catalyzed rate is a larger number than the uncatalyzed rate, right? All right. So both of these values should be large for a good enzyme. So now if we look at some examples of Kcat and Km, go back to our carbonic anhydrase, and look at the carbon dioxide substrate, which had a crappy Km, 12 millimolar, but it had a really good Kcat. And so its catalytic efficiency, or Kcat over Km, it's really pretty good. It's 8.3 times 10 to the 7th, which is only surpassed by one of the world's most perfect enzymes, acetylcholinesterase. Okay, and acetylcholinesterase has a Kcat over Km of 1.2 times 10 to the 1.6 times 10 to the 8th, which is one of the fastest. Here's another one, triphosphate isomerase. Our Tim barrel protein has another perfect catalysis. Okay, don't memorize these numbers. I'm just showing you how it's not enough to have just a good Km. We can look at some of these that have really good Kms, like, let's see, well, all of these have good Kcats over Kms, but you can get a good Kcat over Km by having a very small number for Km, despite the fact that you have a kind of small number for Kcat, right? 10 to the 6th is a million, whereas fumarase only makes 800 products per second, right? And yet it has a really good Km of 5 times 10 to the minus 6th. So you can achieve, almost perfect catalytic efficiency either through having an excellent Kcat and a crappy Km, like carbonic anhydrase, or a crappy Kcat and an excellent Km, like fumarase. Okay, so that's the lesson I want you to take away, is that neither one of those constants alone can tell you whether you have a good enzyme. You must look at the ratio of both the chemistry and the binding.